So the way that we would start an ice table like this, and we have gone back to ice tables, is calcium phosphate, of course, is a solid. It's trying to dissolve. You've got the calcium, which does not have an initial concentration, and then the phosphate ion, which is already there because this is not pure water it's dissolving in. It's a solution of sodium phosphate. So we're given the K value of the calcium phosphate, which we need. You can't end, I mean, this thing is not at its final concentrations because you can't finish with something having a concentration of 0. So it has to shift to the right as this change happens. So that means this side goes down by x, and the right side, the calcium goes up by 3x to 1 to 3 ratio, and then this phosphate is going to go up by 2x. So that at equilibrium, the calcium phosphate is a solid, it doesn't have a concentration, and then the calcium is 3x, phosphate is 0.2 plus 2x. Now is x going to be big compared to 0.2 or small compared to 0.2? It's very small. Look at that K value, 10 to the negative 32nd power. That's a small K. So we know that x is going to be a very small value. So it goes like this. KSP equals calcium concentration to the 3rd power, and multiplied by phosphate concentration to the 2nd power. And we know those values. We can go ahead and plug them in. Calcium was 3x to the 3rd, and the phosphate is 0.2 plus 2x to the 2nd power. And we just discussed that this plus 2x part, because x is so small, that it's negligible compared to 0.2. It's not going to be anywhere close. Now be careful with that cube term in there. Yeah, Mark?
For the, because you neglected the 2 because it's so small, is there like a break-off point for the K that if it's like at a certain point?
No, because the K really kind of depends on how many ions it breaks up into. The solubility, the X term is going to be on the order of like 10 to the negative 6. Because you're going to see how you give off 5 ions?
Yeah.
You're going to take the 5th root of this number is 10 to the negative 6. But compared to 0.2, that's minuscule. Okay? So the answer would be you'll take that K and take the root, whatever root is the same as how many ions it gives off.
So you almost always neglect that?
Yes.
Plus.
Yeah, neglect the change.
Okay.
Yeah. Okay, so mathematically this turns out to be very easy. We do know what the K equals. It's equal to the 1.3. So this equals 1.3 times 10 to the negative 32. And so we have an X expression. We solve for it. What is 3 cubed? It's not 9. It's 27, right. So this is 27x cubed times 0.2 squared equals that. And so you solve for x. You wind up taking a cube root at the end. And you get like 2.3 times 10 to the negative 11th, if I remember right.
Yep.
Now, I want you to keep in mind, I should have mentioned this before. The question is, what is the solubility of calcium phosphate? Remember that the solubility is that term right there, the amount of solid that dissolves. And it is a molarity unit, because as that goes, as this transfers to the right, that's the amount of calcium phosphate that is dissolved. So that's the solubility. Now, if this was just in pure water, it would have gone a lot farther to the right. This number would be several powers of 10 higher. Like, it would be 10,000 times higher if it didn't already have phosphate present. But the phosphate presence does mean that it shifts to the right not as much. That's what happens with the common ion effect. Anytime you already have one of your ions present that something is trying to react and make, then it's not going to go as far to the right because it will get to equilibrium soon. Anything for me about that? Okay. Let's go to the next one. Now, I'm going to just let you chew on this for a couple minutes. I want to see if you can come up with how to do this one and come up with an answer. So I'll do this much. Here's our chemical equation. I'm hoping you have that. Ugh. This looks like ugly math. I hope to not have to do all that.
I got rid of that. Is that allowed?
Which did you get rid of? What's in the
That.
parentheses or the 3x?
The parentheses.
Why? Because it was so small?
Yeah.
It turns out x is pretty small too. This thing breaks up into, this breaks up into 4 ions. And so if you take the 4th root of that, you'll get something like 10 to the negative 9th.
Oh, yeah.
So,
So
I don't know if we can neglect the x, and I don't know if we can neglect that. Does anybody have a way out of this? There is a way out. Look carefully. What, Shane? Cube? No.
Cube root.
Because you're going to have x to the 4th over here. You got these 3 x terms and then that x term too. Let's say a lot of Matthew. We can neglect something? Well, you know what? There's something else here I was hoping you'd see. It's just subtle. This thing right here. What does it mean to be buffered? What about the pH? is going to stay steady. Yes? So if it's buffered and the pH stays relatively constant, then what does that mean? This term is not going to change very much. It's going to keep at a pH of 5, and therefore, even if you have a little change in X, it's buffered, so the hydroxide concentration is going to stay the same. Yes? Ooh, that was nasty. So that means this term right here can be neglected. And that is going to make our math ultra easy. Okay? And again, we only could get away with that because of that word right there. If it said an initial concentration or initial pH of 5, but it didn't say it was buffered, then we would not be doing so well. In fact, you wouldn't even have the problem. You wouldn't even have to do it. But because it's buffered, you know that this term is going to stay constant. It's going to be a constant concentration. So, now that we have gotten rid of this plus reactant, what do we have? We've got 1 times 10 to the negative 9 cubed, which is easy, times x. So, Hel?
Where'd you get the 1 times 10 to the negative?
Oh, because the pH is 5, that means the hydrogen concentration is 10 to the negative 5th. Right? Negative log of that number is 5. And therefore, the hydroxide concentration is Kw divided by 2. That's how I came up with that. So, doing the math on this thing, the KSP is given. It's 4 times 10 to the negative 38. And over here on this side, we have x times 1 times 10 to the negative 27. So just divide out the 1 times 10 to the negative 27. And x equals 4 times 10 to the negative 11. Molarity. Yes. No, this is not hard. This thing right here, that cubed is 10 to the negative 27. So 10 to the negative 38 divided by 10 to the negative 27 is that, 10 to the negative 11. That's what you got too, right? In your head? Shane? You should. Oh my goodness, it's almost time to go. I had one more slide to do with you. Too much lab talk. Should we call it good for the day?
Mm-hmm.
Okay. So this was very short because I let everybody, well, we talked about the quiz. I gave back the quiz. And then we went and I gave everybody like 20, 25 minutes to work on the lab. So that was what was left over.